Okay, now this discussion is going to continue to parallel our discussion of injective linear transformations. We noticed that injective linear transformation preserved the idea of linear independence. Now, it turns out that surjective linear transformation does not necessarily preserve linear independence, but it does preserve the idea of spanning. Now, these two things come together in the case of a basis, right? Basis is a linearly independent set that spans. So injective guarantees linear independence. Surjective guarantees spanning. So you'll see later when we have transformations that are both injective and surjective, then you're going to see that the basis property is also preserved. But that's for the next chapter. All right, so the theorem at hand now is to show that if I have a spanning set, this is not necessarily a basis, but is a set that spans U. That means that U is equal to the span of S. I don't need set brackets because the set brackets are here. I could say, or U is equal to U1 through U, what is that, T. Okay. Now if that's true, then if I take the image of S, image of each vector in S, U1 goes to TU1, U2 goes to TU2, etc., UT goes to TUT, then this set R spans the range of T. So that means that the span of R is equal to the range of T. Or I can say that the span of R is equal to the span of TU1 up to TUT. Okay. And this makes a lot of sense. And since you're trying to show that two sets are equal, you're basically trying to show that the span of R is equal to R of T. You need to show both ways. You need to show that R of T is contained in the span, and you need to show that the span is contained in R of T. All right, so let's begin with proving that R of T is contained in the span of R. So let's choose any V in the range of T. Then there exists a vector U that maps to V. Since this U1 through UT is a spanning set, I can write this arbitrary U as a linear combination. If I take T of both sides now, I know T of U is equal to V. If I take T of the right-hand side, by using linearity property, I get that this is a linear combination of TU1, TU2 up to TUT. So in other words, V is in the span of TU1, TU2 up to TUT, which is exactly what I wanted to prove. On the other hand, if I have something that's in the span, I can write it in such a way. I can use the linearity property to show that V is T of this vector in U. Okay. So that means that T is in the range of, that this vector here is in the range of T. So we're fine. So V is in R of T. So we've shown both ways that the range of T is exactly the set that's spanned by R. Okay, so this is an easy way to provide the construction of a basis, because we can find a spanning set, and if you have a spanning set, then you can find a basis from that by doing the same procedure we did before. Change the column vectors into row vectors and then row reduce. All right, so let's look at this example, finding the basis for the range of the following linear transformation. This maps 2 by 2 matrices into polynomials according to this rule. All right. Now we can choose a spanning set for the domain, which are these elementary matrices here. And that means that this gives us a spanning set for the range. Okay. Now you can compute T of 1, 0, 0, 0 according to this rule. That's just going to be 1 minus 3x plus x squared. T of 0, 1, 0, 0, well, I find all the places that have b and set b equal to 1, so that's going to be 2 plus 2x plus x squared, and so on. Okay, so here we have a spanning set for the range. They may not be linearly independent. So we can see that he shows that these two are actually linear combinations of the other two, so we can remove those. It's clear that these two are linearly independent because they're not scalar multiples of each other. So the dimension of the range is 2, and here's a basis. Okay. All right, so here's another way of expressing range. A vector is in the range if and only if T inverse of V is not empty. All right. And I think that's just basically the definition of range. If something's in the range, then there's some V that maps to it. And that's the same thing as saying T inverse of V is not equal to 0. On the other hand, if T inverse V is not equal to 0, then something maps to it and you're okay. Okay. Now we've been talking about range in general. Now for surjective linear transformations, the range is equal to the codomain. Okay, so what we said about ranges above, when we said that here we said that the image of these the spanning set is a range spans the range. In the case where the range is the codomain, we know that the images of, for instance, if we choose a basis here, the images of the basis vectors must span the codomain. So that's what we're talking about down here. All right. So here we have, if we have U1 through UM, and you take the images of those. Now, if T is surjective, this must span V. On the other hand, if this spans V, then for any vector in V, you can find a vector in U that maps to it. So surjective is the same thing as saying that you have a spanning set for the codomain, which is based on the images of a spanning set of the domain. So what does that tell us about dimension? Suppose the first set here, the U's, is a basis. Okay. We know that the image of a basis, if the transformation is surjective, then the image of a basis also spans the codomain. So we say the image of a basis of U spans V. Now, what does it mean that it spans V? It means that we can take a subset and get a basis. So that means that the number of vectors in the basis of V must be less than or equal to the number of vectors in the basis of U, because I can take a basis of U, get a spanning set, throw out some of those vectors, and get a basis. So do you follow that? You follow that the number in the basis of U must be bigger than or equal to the number in the basis of V. So that means the dimension of U is bigger than or equal to the dimension of V. And that's the content down here. If U goes to V as surjective, then the dimension of U is bigger than or equal to the dimension of V. And this argument basically recaps what I mentioned. So we have some examples of this as well. Finally, again in parallel to the injective linear transformation discussion, we can show that the composition of surjective linear transformations is surjective and has a similar proof and has the same flavor proof that if you have two functions, And you have a composition of onto functions is onto. So I'll let you read that proof, and here we'll stop the discussion.